Assalamualaikum warahmatullahi wabarakatuh. My name is MALEK TANZEE bin REDZUAN, metric number AA211463. Today I will present about closed loop system 1 in this project. Okay, this is closed loop system 1 that I use. Moving on to system 1. Okay, for objective 1, this is the mathematical calculation that I use to determine poles and zero to sketch the pole zero plot for the closed loop system 1. First of all, this is GS that I get from the closed loop system 1, which is 1 over S square, HS, which is 1, and I use TS equal to GS over 1 plus GS HS. Then I put the values, and finally I get 1 over S square plus 1. So 1 is the numerator, which is mean it is the zeros, and S square plus 1 is denominator, which is poles. So the zero in this closed loop system, there is no zero because no S in the numerator. For the poles, S square plus 1 is equal to 0. S square equal to negative 1. So S equals to set negative 1 J. Finally, S equals to plus minus J. Okay, this is the pole zero plot. As we can see here, J and negative J is in imaginary axis. So I plot it in this imaginary axis. Okay, moving on to the number 2. This is the result from MATLAB software using PZMap instruction. As you can see here, the pole is 0 plus 1i, and the second pole is 0 minus 1i. Based on the result that I get in activity 1 and activity 2, both of the activities have the tally result. So the characteristic of the system is marginally stable since the poles are on the imaginary axis. Moving on to objective number 2. This is the step response for the closed loop system 1. I'm using command Windows to get this step response. Next, this is a table of MATLAB result from the closed loop system 1. From the diagram and the table above, this is the data that I get using MATLAB software for the closed loop system 1. The closed loop system 1 is undamped, where the characteristic of this step response is marginally stable. The result of overshoot, rise time, and settling time are none or not a real number. So the steady state error that shown in the table is positive infinity. Moving on to objective 3. For this objective, the PID values that I use are KP equals to 30, KI equal to 6, and KD equals to 300. The results are shown in the table below. So for the PID controller, the step response is like this. Okay, for the overshoot, I get 0.0308%. For the rise time, I get 0.0073. For the settling time, I get 0.0130. And finally, the steady state error is 0 because the final value here is 1. 1 minus 1 is equal to 0. For the PI controller, the overshoot, rise time, and settling time is none. And the steady state error is positive infinity. For the PD controller, the overshoot is 0.0306%. For the rise time is 0.00373. The settling time is 0.0130, and the steady state error is 0 because the final value, the steady state value is 1. 1 minus 1 is equal to 0. Finally, the P control, the overshoot, rise time, and settling time, and also steady state error get the same result as the PI control, which is none, and the steady state error is infinity. Okay, this diagram above is the combination of all step response where the T is without a controller, T1 is a PID controller, T2 is a PI controller, T3 is a PD controller, T4 is a P controller. As we can see in the diagram, the characteristic of T1 and T4 are unstable because the result of the calculation are undefined, which is none or not a number, and for the steady state error is positive infinity. For T1, the step response is underdamped where the characteristic is stable. For T3, the step response is also underdamped where the characteristic is also stable, which is same for, as T1. As we can see in above, T1 and T3 are overlapping each other because of their overshoot is same, because their overshoot value is nearly the same. So for the closed loop system 1, the controller that produce stable characteristic are PID controller and PD controller with a nearly same overshoot values, which is 0.0308% for PID controller and 0.0306% for PD controller. The most suitable controller is PD controller because it's used two controllers, which is less space is used and less likely to oscillate and overshoot. Okay, finally, for the conclusion, based on the activity performed in Objective 1, 2, and 3 of the closed loop system 1, in Objective 1, I can determine the stability of a closed loop system 1 using mathematical calculation to obtain poles and zero and also sketch pole zero plot for the system. Then, I was asked to use MATLAB software to confirm the answer of my calculation using PZMAT instruction, and I managed to get the same answer. Next, for Objective 2, I managed to simulate the closed loop system 1 to obtain the step response and get the value as the question asks. Finally, for Objective 3, I managed to find the controller that meet the control system design requirement using the KP equal to 30, KI equal to 6, and KD equal to 300 values. All the activities using the same time, which is T equal to 0, 0.01, and 10. I can conclude that from this project, I managed to solve all the questions given in this project. I managed to solve all the questions given in this project, inshallah. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AKIF FAISAL bin ARMAN. My matrix number is AA2894. So today I want to present about System 2, Closed Loop System 2. So this is the question. The transfer function is 20 over s squared plus 2s plus 9. So for the objective 1, for Closed Loop System 2, this is the mathematical calculation. So this is the mathematical calculation that I use to determine the pulse and 0 to sketch the pulse 0 plot. So I sketch the pulse 0 plot. This is the pulse 0 plot. So the result from MATLAB using PZMAT instruction. So this is the common window. So the result from MATLAB is here. So by referring to the pulse 0 plot, we can determine that the closed loop system for number 2 is stable because it's same in the mathematical calculation. So it's the stable. So for objective 2, set response for the closed loop system 2. This is the graph for objective 2, step response. So for the system closed loop 2, we can see the shape of the graph. So the graph is underdamped. So the system is stable. From the table above, we can see that the table shows the value of the overshoot, rise time, setting time, and the last one is steady state error. The value of the overshoot is 25.2080. The value of the rise time is 0.2224. The setting time is 3.7156, and the last one is the value of steady state error is 0.31. How to get steady state error? Because 1 minus the final value 0.69, so that we can get 0.31. So for the objective 3, for this objective, the PID value that I use is KP equal to 13, KI equal to 6, and KD equal to 300. The results are shown in the table below. So this is the result for PID controller, PI controller, PD controller result graph for controller, and last one is P controller. So in this diagram, we can see that This closed loop system too is suitable to use PID controller. It because PID controller is the best controller to optimize the closed loop system. Number two, because the overshoot value is 0%. We can see at the graph. So overshoot for the PID controller is 0 and the statistic error is 0. So that's why it suitable to use. That's why system 2 is suitable to use PID controller. Also, the steady state error is 0. It's lower than steady state error for the controller PI, PD, and P because we can see at the graph PI, the steady state error is 0, and for PD, the steady state error 0.015, and for the P controller, the steady state error is 0.015. So, PID controller also meet the requirement for overshoot, setting time, and steady state error value. So for the conclusion, based on the work done in the system objective 1, 2, and 3, I can assess the stability of a closed loop system is using mathematical calculation to produce poles and zeros, as well as sketch a pole zero plot for the system. I was then instructed to use the MATLAB program to verify the result of my calculations. Using the PZMap instruction, and I was able to obtain the same result. I was then able to simulate closed loop system 1 for objective 2 in order to obtain the step response and the value specified in the question. Finally, using Kp equal to 13, Ki equal to 6, and Kd equal to 300 values, I was able to identify the controllers that satisfy the control system design requirement for goal 3. The total time spent on all activity is t equal 0 equals 0.01 equal to 10. I can draw the conclusion that I was able to answer every question in this project. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rahimi ROSLAN. My metric number AA212713. So, this is my system 3, control system project. Objective 1, mathematical calculation using characteristic equation to determine the poles and zeros. So, first, GS equal 0 over S power of 2 plus 4S plus 50. And HS is equal 1 because it is unity feedback. Transfer function equal, this is formula, GS over 1 plus HS GS. So I put the number from this formula. So this and I get zeros and poles, and I put this number to this formula. A equal to 1 because S power of 2, and B equal 4, C equal 300. So after that I get S1 equal negative 2 and S2 negative 2. So from this equation, from this answer, I sketch the plot, closed loop system 3. There is poles, 2 poles and 0 zeros. So from MATLAB, I do some command to know the answer is tally to my result or not. So this result from MATLAB. So based on what you can see from my calculation and MATLAB, it is same answer. So the system is stable because pole on the left side and the axis and y axis both zeros at s equals 0. So objective 2, the result from MATLAB using the instruction. Go to MATLAB. Okay, this is how I get the answer. So I use command G equal transfer function 250 1 4 50. So this same to my system. Okay, if you can see, okay, this is my system, same as my MATLAB. So H equal 1, T feedback GH. So I get this. This is same for this same from my calculation. So after that I get this graph. So the final value is equal 0.833. So how do I get steady state error? 1 minus 0.833, so I get 0.167. So this system is stable because as I can see from the graph, this graph is stable. Okay, for objective 3, implement P, PD, PI, PID controller to meet control system design requirement. So the design requirement is overshoot below 10%, center time below 5 seconds, and steady state error below 2%. So how I do this objective, I use this editor, so it is more easier for me to get answer. So I use P equal to 30, KD equal to 300, and KI equal to 6. This is my transfer function. As you can see, this is my transfer function. So first I make PD. PD is equal KD KP, and PI KP KI. Lastly, PID equal to transfer function D P and so this is how I coding from the editor MATLAB to get answer. So I can show you example how I get the answer. So example, I uncomment comment and uncomment P, PD and PI. So I want PID. So if I want PID, I just uncomment PID and run. So if I run the system, I get graph from MATLAB. Okay, as you can see, this is my PID system. The steady state error is equal 0, certainty time 5.2192, exponent negative 0.5, last time 2.9298, exponent negative 0.5, and overshoot is 0. So this result is telling what I want from design requirement. We go through PI. So example, I want PI. I just comment this PID and uncomment PI. Okay, so I comment PI. So I run. So if I run, I get this graph. Okay, PI. So this is PI graph. Same as my report. So I will shoot 0. Last time 2.5978, exponent 0.4. Settling time none, and steady state error 0.032. So this PI controller not very good to I choose because the settling time is none. So we go through the PD controller. So PD controller, I comment this, comment and uncomment this. So I run. So after I run, I get this graph from PD controller. So this same for my report. So I get steady state error 0.007 and certain time 4.8438, last time 2.8538, and overshoot 0.5560. So based on design requirement, the overshoot is good. Center time we get less 5 seconds, so good, and steady state error less than 2%. So PD controller is good. So we go to P controller. P controller same from MATLAB. Just comment this, just uncomment and comment this. So I run. So I get this graph. So this graph is same as my report. So I get steady state error 0.007, certain time 1.956,
0.029, last time 0.0122, and overshoot 93. So it quite big, so this controller will reject. So the best controller is BID. Overshoot 0, last time 2.929, setting time quite good, steady state 0. So the based on design requirement, PD controller is suitable because overshoot and below 10%, last time certain time below 5 seconds, and steady state error below 2%. So the conclusion for my controller system, system 3, I know how to use mathematical calculation determine the stability of closed loop system, and I obtained how to pose and zero, how to sketch plot, and then how to use MATLAB to confirm my calculation. After that, I also can simulate the closed loop system to get step response and find controllers that meet the control system design requirement by using the value KP 30, KI 6, and KD 300. So the same the activities were done over the same time period of t equals 0, 0, 0.1, 10. So based on P, PD, PI, PID controller that I get, I think PD controller is best controller that I get based on design requirement. So thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amin HAIKAL bin Halim. It is number 881 we explain the system for in closed loop. Okay, the first one is objective one. So this is a mathematical solution that I do. First one, I transfer function the function of g and t, and the numerator and denominator. We can get the s is equal with -2, and denominator we can see the x1 equals negative 810 0.316 plus imaginary number 0, x2 1.0258, imaginary number 8.3713, x3 equal with 10258 minus imaginary number 8.3712. And the second one, for the using the physics net, we can get the value on the graph is same with the mathematical solution. Then move on to objective 2. We use the move on to going to objective 2. This is a simulate the closed loop system to obtain the step response. Okay, we can see the closed loop system 4 is unstable. It is because they have an overshoot, rest time, and settling time. This is because the rest time is required for the response to rise from x% to y% of its final value, and the meaning of the rest time is a low value to a specific high value. So the setting time is the time when to start response, which is and stay within 2% of its steady state value, and the steady state value in the system is going to infinity. The steady time will come up with the unknown value. Which that reason the value of the overshoot also undefined, because the value of the overshoot is referring to an output ascending is final. It is a steady state value. And we can see if the use the time 0 to 60, the graph which will show to the state going to straight and go to oscillation. After if we using the smaller scale, it will also going to wave and going to infinity. So we going to the largest also. They will also going to waste to going to infinity. That's the reason the steady state value is undefined. Okay, going to objective 3. This is a implement P or PD or PI or PID controller to the control system design requirement. With the objective 3, we must establish of the system going using the controller. The first one, which is the P controller, we can get the overshoot is a 39.6, price time 0.184, the settling time 1.95, and steady state error is 1. For the overshoot is quite big for the system, and the final and the steady state error is also big because of we need a steady state error is near to 0. Okay, going to the PI controller, we can see the overshoot is 105 and the steady state error is 0.614, and we can see the overshoot is bigger than the P controller, but the rising the rise time is reduced from the P controller. Okay, going to the PD controller, we can see the overshoot is going down, going to the 39.6, and steady state error equal with 1. And we can see the overshoot is reduced, but the steady state error is equal with 1. That is not good for the system. Okay, going to the PID controller, we include the I in the control. Now we can get the overshoot is 0.7905 and steady state error is 0. But the rise time is increased, but the overshoot reduced. So this is system have the stable other than that and suitable for using in the future. Okay, the value used in the closed loop system 4 for KP is 0.000001. If the value is increased, the graph and the value of the number will change and the smoothness of the graph will not be the same as before, the default of our KP. If we decrease the value of the KP, the graph will remain the same as the default. The value of the KI in the system 4 is 0.12555. The value is suitable for the system after several trying to get the best value like that, like in the simulation in MATLAB. The last value of the controller KD is a 0 because the value will appear in the stable graph with lowest overshoot, and that's we can get. In the final controller, we use to stabilize the system by combining the controller KP, KI, and KD to going to be PID. The value of the controller PID will show the most stable system, smooth graph, and have a 0 steady state value to give a highest efficiency in the system.